find yourself trapped in some weird room. You are also told you can start at any platform as long as you collect every diamond. Where should you start? What path should you take? Suppose we start here. Now let's take this path. Seems the route we took can't reach the last bridge and collect the final diamond. Is there another path we could take? Suppose we take another route starting from here where we left off. That didn't seem to work either. Is there some way we can figure out where to start or what path to take? Let's look at a similar situation. We have 4 platforms to start from and 4 bridges connecting them. Does it matter where we start here? The routes all look similar. Let's test a path to see what happens. Not only did we collect every diamond, but it seems we have also ended up exactly where we started. In this case, how did we manage to collect all of the diamonds, but we couldn't with the other set of bridges? Look at this layout of bridges and platforms. Let's test a path and start at the larger platform. Starting here, we couldn't cross every bridge and collect every diamond. Before we move on, let's try another platform to start on. It seems that if we start at this platform and follow this path, we can cross every bridge and collect every diamond. So how would we know what path to take or platform to start at without testing each option? Before we start, let's simplify the scenarios. We can do this by simply drawing platforms as circles and lines for the bridges. Let's also establish some terminology. We will call the paths we take edges, and the platforms will be referred to as nodes. Let's draw the pattern for 3 of the scenarios we've encountered. Before we take a look at these, let's look at some simpler diagrams where there are only 1 or 2 bridges. How do we analyze these? If we have 2 nodes and only 1 path, no matter what node we are on, we will end up at the other node. If we had 1 path next to it, we'll have this new diagram. In this example, we see that we end up exactly where we started. In fact, if we have an even number of paths, we will always end up where we started, and only once. We call this path we took Eulerian. The example where we started and ended on the same node is called an Eulerian circuit. So how do we know if it's Eulerian path, Eulerian circuit, or neither? Well, all we have to do is look at every node and count the number of paths that are connected to it. We will then identify if the node is either in odd order or an even order. If we take a look at this example here, if we look at each node and count the number of connections, we will see that there are 2 edges that connect. This alone tells us that if we start at any node, we will end up exactly where we started. This is known as an Eulerian circuit. Now, saying that, having an even number of connections on a diagram results in an Eulerian circuit can be a bit hard to explain, but we can think of the edges as canceling out. So if we need an even number of edges on each node in order to cross every edge only once, why? Well, simply put, there's an exception to this rule. There can be an odd number of connections on a node, but there can only be 2 nodes with an odd number of edges. This is not an Eulerian circuit, but just an Eulerian path. In addition to this, if we want to cross every edge exactly once, we have to start on one of the nodes with an odd number of edges. To see how this part works, we can look at the diagram as it was shown earlier. This diagram has 2 nodes with an odd number of edges. We can try to cross every edge if we start on a random node, but we can only cross every edge if we start on one of the nodes with an odd number of edges. In other words, we can check if we can cross every edge exactly once if the diagram meets certain conditions. Does every node have an even number of edges? If yes, it is an Eulerian path in a Eulerian circuit. If there are nodes with an odd order, there can be only 2. If there are not 2, then it is not possible to cross every edge once. Now that we have this knowledge, let's apply it to the scenario from the beginning of the video. Let's construct the diagram for this. Now let's go to each node and count the number of edges connected to it. Let's first check if all nodes have an even number. We see that there are odd numbers present, but odd numbered nodes can still be possible if there are only 2 odd numbered nodes. This diagram has more than 2 odd numbered nodes, which tells us that we cannot start at a node and cross every edge only once. The example we worked out has a significant role in mathematics. This particular problem is known as the 7 bridges of Königsberg. A man wanted to know if he could walk across each bridge only once. To see if this could be done, the problem was sent to the mathematician Leonhard Euler. After working with the bridges, he wrote the checklist that was used in this video, although ours is a bit more simplified for the sake of understanding. While this question originated from a person wanting to take a walk, this was a step into the branch of mathematics called graph theory. We see this branch of mathematics take a hold when we want to use a navigation system. We may not use it directly, but it does play a role in our lives. I have a challenge for you. There was a photo of a house layout that circulated the internet a while back. You may recognize it. The challenge is, can you take the edge that goes through every doorway in this house exactly once? What would the diagram look like? Is it possible to cross every edge exactly once, and why?